Okay, it's 2 o'clock. My name is Ilya Sinaisky, and I'm one of the lecturers for this summer school. And my lecture will be tomorrow on some computational and theoretical aspects of open quantum systems. And today I'll just step in for Francesco, and we'll share this afternoon session. Francesco will join us later. And I'm very happy to present to you Charles Crosby, who will tell us about computational fluid mechanics. Thank you.
Thank you, Ilya. Righto, my name is Charles Crosby. I am a research scientist at the Center for High Performance Computing in Cape Town. You all know the history of the CHPC by now, so I'm not going to carry on about that. We as research scientists are there to support primarily the users in the various scientific disciplines on the system. And together with Andrew Gill, I have the responsibility mainly for computational mechanics. My own field is computational fluid mechanics. I've been in it for quite a long time. In fact, I was involved in it already before it was even called CFD. So I'm not going to give you a theoretical series of lectures. That's what universities are for. Also, as Ilya referred to the textbooks, where I'm not going to give you a list of textbooks either. Any university library will have several very good textbooks on computational fluid dynamics. What this lecture series is intended to do is to almost point you in the direction of the things that you need to learn if you want to start doing useful things with computational fluid dynamics. So that's why I've called it an introduction to practical or applied computational fluid dynamics. I've worked in several different places in my career. I've spent 8 years or so lecturing at a university, so I've got my own particular lecturing style, which is very strongly dependent on being aware of what the audience is doing and thinking. And this is quite awkward really in a virtual platform like this, because I cannot see your faces. I cannot see if I'm putting you to sleep. I've got no idea how you're reacting. So I would really like to encourage you to react. I expect you to react. If you're not reacting, I'm assuming you're asleep and you shouldn't really be here. So please feel free to raise your hand even during a lecture part. Andrew will draw my attention to the fact that a question has been asked, and we'll stop the lecture there. And if it's relevant, we'll discuss it right there and then. So the way I've structured the lectures is for each of these 3 lectures this week, I've divided them into 3 micro lectures each, maybe 10, 15 minutes or so, depending on how things go. And at the conclusion of each of these micro lectures, we're going to just have a chat about it. And I would really appreciate it if people actually took part in the chat. I want to know how you've experienced it, whether you'd like me to go into more detail on some of the aspects, or whether you'd actually even like to differ from me when it comes to any of those. In terms of my own career, I did my stint teaching at university, but then I've also spent a lot of time working in industry, in various industries. I've been involved in the design and development of unmanned flying vehicles. And I've also been involved in the design of competitive racing yachts. And all of these made a lot of use, very intensive use of computational fluid dynamics, because they taught us so much about what we were trying to achieve in those projects. And it's some of the lessons I've learned from those experiences that I'd like to share with you today. So I'll share the screen with you now so we can get into the PowerPoint presentation. Can you see the presentation?
Yes.
Okay, great.
Yep, that's visible.
I just want to get the Zoom session up here as well, so I can follow what's going on. Okay. So Andrew, you'll draw my attention to any questions that get raised. Right. When we discussed the framework that we should follow for these lectures, we kind of came to the conclusion it would be a really good idea to talk about simulations in general, because computational fluid dynamics is a particular form of simulation But the feature of the last 40 to 50 years of science and engineering has been simulation more or less everywhere. So we're starting off with most of today's lecture, these first two lectures, will be about simulations and what you're trying to do with simulations, how you use them, and some of the different types of simulations that you get, and some of the lessons we learn about how to make use of simulations. Then the last of the three short lectures will be a little bit about the different types of CFD simulations. So we're not getting into any real depth on the CFD side today, just a bit of very superficial stuff about the different types of simulations that you can get. Right, so purpose of these lectures, I've alluded to this already. The theory of fluid dynamics is very involved. The theory of computational fluid dynamics is even more involved. If you want or need to get into those, get yourself the right textbooks, but most importantly, get yourself into the right university courses where they can teach you about it, because we're talking about several semester term courses that you need to follow if you really want to get to a fundamental understanding of how CFD works. At the same time, the programming implementation of CFD is also a very, very specialized field, and it's best taught at university or in industry with the companies actually doing development of CFD code. So we're not really going to touch on that now. We'll talk a little bit about how to use CFD software in parallel. This is really a superficial discussion of what you're doing with CFD in research and development. The reason why it's necessary to pay some attention to these things is that you could almost say there's no such thing as routine CFD. You can get to the point with in a certain field where you could say something has now become routine in CFD. But every time an experienced CFD practitioner starts to do something new, he finds new ways in which the software can trip him up. In a lot of fields like structural analysis, for example, you never expect the software to give you any trouble. You expect to plug your models in and get the numbers out. CFD is not like that. Numerical divergence, the program crashing on you, it happens very frequently, and you've got to go back and figure out why it's happening. Are you posing an impossible question? Are you posing it badly? Are you giving it the wrong parameters? It's never that obvious, or it's very often not that obvious. You may need to spend quite a lot of time on getting that right. At the same time, it's quite easy to get misleading results. The fact that you've got a colorful picture showing you regions of high and low speed in your flow and low and high pressures that go along with that, yes, it's nice and it looks nice. Does it actually mean anything? And are you asking the right questions? My personal experience of solving industry problems with CFD has been basically you can believe it, but you have to be very, very careful about asking the right questions. You can certainly ask the wrong questions very, very easily. So a concept that's very important with any kind of simulation or analysis work is the question of fit for purpose. You'll find me returning to this question. What kind of answer is fit for purpose? There's no absolute right way of doing anything in this life. There are different ways, and you've got to find out what's the one that's going to work in terms of getting you to the answers that you need. And this is what I mean by fit for purpose. You may be able to get away with very simplified, very fast analysis, or you may need to spend several months doing a lot of detailed work to get to a single answer. The question is, what are you trying to do there? So I'm trying to give you an overview here of the competencies that you need. You will need to go and learn these competencies if you want to practice CFD. This is an overview of some of those competencies. Right, so optional assignment. There's an optional assignment on this part of the course. You don't need to do this if you don't want to. If you want to learn about CFD, I would strongly recommend that you do this. It's a very good place to start. There's an open source CFD code that's very widely used all over the world in industry and academia called OpenFOAM. If you're a little bit confused about why they call it foam, it's got nothing to do with a substance foam. It's a field operation and manipulation. I think somebody was just looking for a very nice acronym. Like a lot of open source software, this one has broken up into different streams. You can go primarily to two places on the web where you will find up-to-date versions of OpenFOAM. There's openfoam.com and there's openfoam.org. There are historical reasons that we don't get into this right now. The two versions are roughly equivalent. They are not exactly equivalent. So there's a little bit involved in jumping between the two versions. At the CHPC, we support both of these versions. So we have the latest version of both of them. And also there's actually even a third stream, which we're not going to talk about now. So the assignment, get a hold of OpenFOAM, get it installed on your computer, and look for the tutorials directory and pick yourself any 5 tutorial cases. There's literally hundreds of them. They're very easy to run. They've got scripts. You can just say all run and they will run. But try to figure out what they're doing and then use a post-processing program called Paraview to make some plots of these results so that you can try and understand what you've just done. So OpenFOAM is not particularly easy software to use. It doesn't have a user-friendly interface. All the inputs are done via text files. And the numerical stability is not as good as the commercial program. So some good reasons for this, some less good reasons for this. But OpenFOAM is not easy software to use, but the tutorial cases are very easy to use. And it's also very easy to install on Linux, especially if you're using a recent version of Ubuntu. The developers seem to like Ubuntu. So if you're running Ubuntu on your laptop or your workstation, it's quite easy to get that installed. You can also get it installed on the other versions, but it might be a little bit more tricky. Yes, shoot.
Sorry, you should actually interrupt. Somebody asked whether it runs, Rockefeller asked if it runs on a Mac as well. I don't remember actually seeing the Mac version.
No, that's a very good question. I think it might, because the version, look, the simple way of getting around that is to install Oracle VirtualBox and install a stripped down Linux operating system in that VirtualBox. So virtualization, you get yourself a computer within a computer. You can install Ubuntu in there, and then you'll be able to run OpenFOAM quite easily. That will work on a Mac. In this way, you can run on any of these x86-based systems. There's a different way as well. So if you want to run it on Windows, there are 2 different ways for the 2 different streams. So the openfoam.com version, they give you a Docker container. So Docker containers is basically a lightweight virtual machine. And I suspect that Docker container should work on a Mac as well.
I've just checked, there is a Mac version.
Is it?
Docker, yeah.
Docker version for Mac. Okay, brilliant. So you can use the Docker version on the Mac, or you can use the VirtualBox approach with just a Linux with a Linux machine on the Windows machine. And then with Windows 10, you've got the so-called Windows Subsystem for Linux, which is actually a very cool piece of technology. It allows you to install without the heavy VirtualBox environment. You can install Ubuntu or some of the other Linux distributions, and then you can use it just as if it is a Linux machine. So I've tested this last one, the Windows Subsystem for Linux. And it worked without any great difficulty. So that's certainly a viable proposition. The Docker container, oddly enough, I had some difficulties with. I think it may be related to my laptop being very old, because it asked for a BIOS setting that wasn't available on my laptop. Just want to check what's going on in the chat box. Just give me a moment. I just want to get to see if
you were just checking too. You wanted the link, so it's actually on the.
Okay. Now I'm just asked about it. Oh, sorry. I'm just battling a little bit to get the Zoom chat information on the screen at the same time as.
Oh, when you've got it full screen, it's a pain.
Yeah, it's a little bit of a pain. So I'm not quite sure where that's going to.
If it's in terms of compute resources.
Okay. Yeah, so if you would just draw my attention to these questions as they come in, I would appreciate it. In terms of compute resources, I don't know if Andrew's answered that to your satisfaction. Yeah, it's a CFD. It needs lots of computing power, but the tutorial cases are very easy. They're lightweight. So they run in seconds or minutes or occasionally in an hour or 2 because they're all small problems. Right, if we can move on. Okay, so for those who want to get into it in a bit more detail, you've just done the Python course. How you go about writing a simple CFD code. If you've got any intentions of getting into CFD code development, even if it is modifying OpenFOAM or writing a solver within the OpenFOAM framework, which is really what it's intended for, then this link here will take you to an example of how to do this with Python fairly simply, to write a basic or fairly simple Navier-Stokes CFD code. And then taking a different approach, which is not specifically Python bound, is also this link, which will also give you an example of how to write a lightweight CFD program. So if you're interested in that, you're welcome to do that. We're not going to be checking up if anybody does that. Right. Back to the original topic, science and engineering simulations. Wikipedia gives us a definition. A simulation is an approximate imitation of the operation of a process or system that represents its operation over time. So the two relevant things there is the approximate and the imitation. So it's not the real thing. It's a copy of the real thing. And it's not necessarily particularly precise. So how precise it is depends on what you're trying to do with it. It doesn't necessarily have to be that precise. There is such a thing as good enough. We think in terms of simulations being computer-based, like CFD, but for a lot of history, before we had computers, other simulations were used. So you can have physical testing. So from my personal experience, wind tunnel testing, tow tank testing, where you tow models of ships in water tanks to measure the resistance, for example. And one of my favorites, although I've never had the privilege of being involved in it, is crash testing, because it's quite spectacular. And then you can have a combination where you have digital technology and physical technology in a single simulator. So we'll talk a little bit about human in the loop simulation and hardware in the loop simulation, because these are quite important in industry. Right, so to get into one of my favorite kind of testing, this is a full-scale simulation, full-scale crash testing. As usual, it's a YouTube video. It'll take a moment to load. Well, hopefully it will load. It's quite entertaining to spend some time looking at crash tests on YouTube. If there's something that will teach you to drive carefully, it will be crash testing, because it's very often these crashes are, let's shut that up. If there's something that will draw your attention to testing, to road safety, it's crash testing, because these tests are carried out at very low speed, something like 40 kilometers an hour. You almost never drive as slowly as 40 kilometers an hour, but it's spectacular to see how much damage you get. So your immediate reaction may be, but this is a real test. They're testing real cars. Why are we calling it a simulation? It's a simulation because it's happening in a laboratory under artificial conditions. You're not going to drive in real life at 40 kilometers an hour head on into another car. You're going to have some kind of other accident. But the technologies that help to keep cars safe in these kind of accidents will hopefully help to keep cars safe in other accidents. So that's why it becomes a relevant simulation. It's also a relevant simulation, obviously, because of the passengers. We haven't quite got around to using prisoners as crash test victims, so we use artificial people as crash test victims, so we can measure what happens to them. And believe me, if you've ever been in a really big car accident, you'll be very grateful for all the work that goes into modern cars. The difference between old cars and modern cars is dramatic. And this is due to, largely due to the simulation involved in developing better and safer cars, ones that you're less likely to get injured in. You can spend a lot of time watching this, especially how badly old cars react to accidents, but we'll stop it there. Right, so closer to my sort of field of expertise is wind tunnel testing. Now, a normal wind tunnel test is a spectacularly unspectacular event. You've got a model firmly mounted in a wind tunnel, and it doesn't do very much, and the wind blows over it and you measure the forces. Flutter testing does exactly what you don't want wind tunnels necessary to do, which is to destroy the model. If this happens in a normal wind tunnel test, you'd be very upset because you really don't want things flying around at 100 meters per second in a confined space. But dynamic testing, such as flutter testing and spin testing and a few other forms of testing, are very valuable in the aerospace industry. But once again, it's important to understand that this is a simulation. This is not the real thing. So when somebody tells you that your simulation results, your numerical simulation results must match the real world, and they point you in the direction of an experiment, for example, wind tunnel test, that's not the real world. That's also a simulation. It's just a different type of simulation. Right, hardware in the loop simulation. This is less well known amongst lay people, but if you've ever been involved in the industry, you realize just how incredibly important this is. Before you actually take something out into the field, for example, to take it flying, you want to test it as to the best extent that you possibly can. So a flight vehicle would be tested something like this, especially a remotely piloted flight vehicle. You would have your ground station with its radio link to the real hardware, the receiver in the real airframe. And it'll be connected to the autopilot or your controller on board the flight vehicle. And then it'll be connected to a flight simulator that models the motion of the flight vehicle. And it'll be connected to something that represents the physical reality of the control systems of this flight vehicle. In a lot of the testing that I've seen, it was actually done the real hardware. In other words, the control fins on the real hardware had to move as predicted according to the simulation program. So you had all the real hardware involved in this test. The only thing that wasn't quite happening is it wasn't actually flying. It was standing statically on a bench. But this is a critical step, because this is where you eliminate the failures that you would get if you were actually flying it.
Charles, we have a question
Yes.
from the chat now.
Shoot.
He wants to know which type of simulation is more reliable, computer or wind tunnel, or lab testing in general, I guess.
So this becomes almost a religious debate, and it rather depends on which angle you come from and which generation of person you are, whether you've grown up with the experimental testing, whether you've grown up with the computational testing. In practice, it turns out that it's not a valid question. You don't do things that way. You use both. You use very detailed experimental testing to validate the models that go into your computational models. Use your computational models to explore areas that would be very difficult to do experimentally. You try to understand the results that you get from your experimental testing. You try to understand with your numerical simulations, because your numerical simulations give you much more information. It's a simulation, but also, so the wind tunnel test is also a simulation, but it's a different kind of simulation. But it gives you information that the other one doesn't give you, cannot give you. So it gives you information, for example, about what the flow field looks like away from the body. That's quite difficult to do in a wind tunnel. It can be done, but it's quite difficult. So you end up using both of these together, and it comes down to the individuals involved, how you work together, because you gain the value from this technology by using the things together. You don't gain the value by using them in competition to each other. You might choose to do less experimental testing at some stage because you've got better numerical results. So you might choose to test it to skip a complete step. You might choose not to generate a full matrix of output information with a CFD because it's slow. It takes a lot of computing time. Once you've got the wind tunnel model or other model, whatever your technology is, your results can come out very quickly. You can get hundreds of data points in a minute or two. You're not going to get hundreds of data points necessarily in a simulation unless it's a simulation that runs particularly fast. If you're talking about CFD never runs fast. So you're not going to get hundreds of data points in a couple of minutes. So you apply them where they are valid. To come back down to the question of really just what the reliability is. There was a time when you'd automatically say, if the two differ, the two answers differ from each other, you need to go and check the computational results because they're most likely wrong. I don't actually think that's true anymore in my experience. If they differ, you've got to go and look at both. And you may find that there's some fundamental flaws in the experiment that stopped it from giving you representative numbers. As I say, when you've got people working together nicely, those are not the questions you ask. The questions, for example, that I've had asked, which ended up being a very valuable one to answer, was, why do these results at this point start looking weird? Because we've looked at these experimental results over and over again, and this doesn't look right, but we don't know if we can really reject it. By doing the very detailed computational fluid dynamics work, it was actually possible to pick up a lot of work, because it didn't come easily, that there was actually a shortcoming in the way, it was an artifact of the way that the testing was being done. So you could safely reject those results. They were non-physical, but you needed the simulation to actually prove that to yourselves or to everybody else. So yeah, you use the two together. You don't put them in competition with each other. Right, human in the loop simulation, flight simulators and other simulators. Here you're primarily using them to train people how to react to certain kind of routine and non-routine situations. There can be other ways of using the human in the loop simulation. If you see a new airliner being tested on its maiden flight, you'd think that this is a brand new aircraft. They're just going to take it up in the air, prove that it can take off and then land it as quickly as possible and all be very relieved about it. That's not how flight testing works, because by the time that prototype aircraft rolls down the runway, the test pilot has flown hundreds of hours in it in a simulator like this, which is as realistic as they can really make it. So they go straight into the work of getting the test information to prove that this aircraft does what it's supposed to do. And in fact, you'll find that aircraft companies will very often build at most one test prototype. They'll accelerate the flight testing program with 4 or 5 different aircraft, but those will belong to airlines when they're finished with the testing. They've got that much faith in their flight simulation. They do not expect to make changes at that point. So simulators, part of the development program, to get, for example, the flying qualities that they want. We're not going to go into the whole Boeing 737 situation because it's a very good example of people not making use of all the tools at their disposal. Right, combination of human and hardware. So we talked a little bit about it on the previous slide, but this is also quite a useful example. Those of you who like to follow open wheel racing cars will know that there was a time when drivers died regularly. And that mercifully doesn't happen anymore. And they've made the cars safer and safer and safer until they reached the point that one of the few dangers still left was being hit by foreign objects thrown up, for example, by another car having an accident. So that's why you now have structures protecting the driver of these cars. And these structures are getting better, and they're now adding, for example, a windscreen to this, a very thick windscreen that'll even stop small debris. But it's a valid question. How easy is it for somebody to actually drive the car like this? Can they drive a car and still see the track under all conditions as well as they need to? So you do this with a simulator. You've got a simulator that does everything that the car does, more or less, except go around a track. You stick the driver in, you make the modifications to it, and you prove that under different lighting conditions, you've got the vision that you need. Right. Heuristics. For those of you who don't know, heuristic is a fancy word for a rule of thumb. In other words, something that people have learned from experience that you can usefully apply to new cases. So the one I haven't put on here, which should really be there, is the purpose of simulation is insight, not numbers. In other words, you're not doing simulations primarily to stick numbers into a spreadsheet. Yes, that's part of it, but you're also learning about what you're trying to do. So that's the insight part. So along with that goes something that says almost the same thing, which is all simulations are wrong, but some are useful. It's just a question of how wrong they are. So simulation doesn't have to be precise. How precise is precise anyway? It doesn't have to be exact, but you need to know why you're doing it and what you're hoping to get out of it. And that's what makes it useful. If you're working on the basis of what you're trying to get is understanding, the more simulation you do, the better you understand what you're dealing with. and all simulations need appropriate quality control. In CFD, I'm not going to talk too much about quality control in CFD. That's, you can go and get that from your textbooks. But there are standard methods to ensure that your CFD results are as reliable as they can realistically be, which is good. The only thing is you need to apply those methods to all simulations. That goes for experiments as well. In other words, you never ever believe a single number. You don't believe a single number from an experiment. You don't believe a single number from a numerical simulation either. This comes from bitter experience. You have to take the time up front to get things right. And this is something we deal with all the time at the CHPC. You get users coming in with models of whatever, CFD models, other forms of computational mechanics models. It doesn't matter. This applies to all these things. A complicated model is not going to work straight away. It's not going to work straight away, and it's not going to give you good answers straight away. You have to take your time to get it right. You've got to build up from simple to complex and make sure that the thing works from the start. If it doesn't work, you stop right there and you fix whatever it is. You cannot build complexity on top of something that's already broken. You have to take your time to get things right. Once you got it working, you can catch up some of the time that you've lost by getting it right. So for example, parallel processing, as we do at the CHPC, is a really good way of actually making up the time. You can do lots and lots of runs, and you can do them. You can run them across multiple computers, and you can run them fast. It's only worth doing if you got them right in the first place. Do not make the mistake of assuming numerical simulations are cheap and easy. They can be very expensive. They can be very hard to get right. But very often it's still cheaper, not always, but definitely safer than physical tests. People don't easily get hurt during numerical experiments. You can learn a lot from simple simulations. I'll talk a little bit about that in the next micro lecture about the different levels of simulation that you can do. But you have to ask it the right questions. Always comes back to that thing. What are you trying to get from the simulation? And then this is also quite a useful one. You've got different ways of getting answers. You've got simple calculations. You've got very complicated numerical simulations. You've got experimental methods. You've got in the field experience, whatever it is that you're dealing with. If those numbers are not tying up, they don't have to be exact, but if they're not telling you more or less the same story, somewhere something is wrong and you have to fix it. Right, so that's it for this lecture. Chat box.
There haven't been any new questions for a bit.
Okay. Right, so I would like to encourage you now to ask whatever it is you'd like to ask. This is a good time to get some feedback. Are you experiencing this as known to you already, not particularly useful, whatever? I'd like to know. Come on, somebody, do you want to choose somebody?
Rockefeller's asked a question. Is it safe to rely on just numerical simulation to allow product or project to go into production?
Not to start with. I'll talk a little bit about that in the next short lecture, but definitely not if you don't have confidence in it. And building confidence in something like this is something that you have to take your time to do. It's not just you yourself as the analyst or the designer or the scientist in a particular project. There are other people involved as well, and you have to convince them. I think you'll find it a very hard sell to rely entirely on numerical simulation. But what you will find in time is less and less experimental work as you get more and more confidence in simulations that are more and more believable. Anybody else? You all gone to sleep? Yeah, but the amount of, well, yes, it's a good way of putting it, is the question of how bad the potential damage can be. The consequences of failure is important. That is relevant. So one of the ways that we figured out in an industrial design environment that worked quite well is if you knew that there was a good experiment still to happen further along in the project, it was a really good idea to accelerate your initial simulation and experimentation. In other words, you don't do high precision work from the start. You take your chances and you get more aggressive with trying to do things fast and take bigger risks. But that's only if you've got the safety net at the back end of a test that you are really prepared to rely on. Yeah, and as you said, depends on how bad it's going to be. Some products involve human life, some don't, you know, so that makes quite a big difference. Okay, nobody else? Right.
Ah, there's one more.
Okay.
Jax has asked a question.
Yes. Nobody said it was easy to get OpenFOAM working. I said it's easy to install. No, you're not getting assessments. You're doing this for yourself. If you need to do CFD in real life, do this for yourself. If you're curious about it, do it for yourself. It's not a practical task to do this as an assessment in the time it's available, because it's quite involved really to do that. But it's up to you. That's why I said it was an optional assignment. Okay, so I'm going to set up for the next one.
Excuse me, I have a question.
Sure, please do.
Okay, so I downloaded OpenFOAM on my PC. I currently have a Windows PC, and for some reason, when I open the application, I get this PowerShell.exe prompt, and then it just gets stuck at waiting for an IP ...
Okay, so we'll have to talk. We'll have to take that offline, because immediately this gets complicated. This is why we said we'd make this optional. It depends on which method you're wanting to do. You know, if you're going via the Docker installation, or you're using the Windows subsystem for Linux. Either of those methods has got some fairly detailed instructions.
Okay.
Yeah, so you need to follow those instructions.
Okay. I downloaded what's that? Docker Quick Start Terminal. I downloaded that.
Yeah, as I said, yeah, carry on, Andrew.
Now, for those of you who did the Bash and Linux part, there's a reason why we taught you all that stuff. It wasn't just to torture you. OpenFOAM is all command line. You do not use a graphical user interface with OpenFOAM. There's some brave colleagues of ours who are trying to make an add-on for a piece of software called FreeCAD, which gives it a sort of a graphical user interface, but it's limited. But it's all command line. That's why you saw PowerShell.
Yeah. It's remember what I said is your inputs are via input files that you have to edit. Okay, so let me, if you don't easily come right, in next week's sessions, there's 2 sessions next week. In the one session, I will demonstrate the use of some commercial CFD tools. In the other session, I will demonstrate how to do some stuff with OpenFOAM. I'm not going to show how to install it, because how to install it's dependent on the system that you're running on. But I'll show you how to use it. It's not as bad as it looks, but you have to get into the thinking of open yourself a command line, edit some input files, or at least take a look at what's in those input files, and then running it off the command line. But I'll do that next week. In other words, remember there's no assessment to this here. You're doing this for yourself. So I'll demonstrate how to use OpenFOAM, but that will be next week only.
Thank you.
Good. So we'll just share this next presentation. I need to get into the Zoom interface. Right, you should be able to see that, the lecture on the importance of simulation. So this carries on really about what we have been talking about so far. It's just in a little bit more detail. Thanks, Ilya. Right, so the importance of simulation. So we've already actually spoken about much of it, but let's carry on here. Right, where is simulation used? So we've already spoken about some of it, of course, but to break it down a different way: research, forecasting, product development, training, entertainment, education. So research, nearly all CFD use in South Africa is in research. It's not so much use in product development because South Africa is a somewhat deindustrialized country. So there's not that much product development going on. So we have an ongoing battle to convince people that it's a valuable tool in product development, not only in research. But it is widely used in research, and rightfully so, because you learn so much. You learn so much from it. This is where you learn to understand things and find better ways of doing things. Forecasting, different types of forecasting. My climate colleagues wouldn't necessarily agree with me, but climate models, weather models, are very, very, very similar to CFD. They're basically doing the same thing, but starting from a somewhat different point, and then with a surprisingly unshared history. The climate and weather modeling sector has developed its own methods that end up looking a lot like CFD codes, but they've taken a different path to get there. But fundamentally, you're solving the same equations on the same computers using the same tools. So weather forecasting, ocean models, typical forecasting models. Product development. So I'm going to spend most of the rest of this lecture actually on the implication of simulation technology on product development. Training is actually very, very valuable because you can try things in simulation that you couldn't do otherwise. So, for example, the fluid dynamic equations, the Navier-Stokes equations, are quite difficult to understand. You can solve them analytically by hand for certain very, very simplified cases where you can say a lot of this is not important. It's either small or it doesn't going to make any difference, or it's not involved in this particular situation. And those are things like, for example, flow between two plates, very low speed laminar flow between two plates, and a few others. You can get analytical solutions. But basically, it's not so easy to understand what fluids really do in practice. But once you've got them simulated in CFD, not only do you get the numbers that you need to start doing useful things, but you actually start to understand what fluids do. And that's very, very valuable. Of course, there are other forms of simulation which really contribute to training. So we've talked about flight simulators. Those are very valuable. Lots of other sort of ways of training people for various purposes, like, for example, medical operations and things. You're now getting to a point of having working simulations of operations. It's a much better way to teach a doctor than to go and cut up an otherwise healthy person. Simulations, of course, have got great value in entertainment. Lots of people play with flight simulators or racing simulators or football simulators or whatever. It's got great entertainment value, and it's also got great education value. That's somewhat related to the training, so we don't need to expand on that. And then, of course, there are certain people who believe that actually we may be living in a simulation. It may not be possible to prove that we don't live in a simulation. I don't believe it myself, but I know that there are people who do believe this, so I'll just leave that there. Right, product development. So product development turns out to be much, much, much more difficult and much, much more expensive than people realize. And the reason for this is that you've got an exponential growth in expenditure during the lifetime of a product development. So I had this explained to me at a conference once in a very simplified form, which I think, it's a simulation of reality. It's a way of looking at reality without being overwhelmingly complex, but hopefully providing some kind of insights. And it's got to do with the fact that as you get further along the process, your costs go up very dramatically, literally exponentially. People use the expression exponentially normally incorrectly. When you start using it correctly, it gets very frightening. So it's quite easy, if you've got a bright idea, to develop a proof of concept prototype. In other words, you've got some clever idea of doing something. So my last job before I joined the CHPC was working on the development of equipment to treat ballast water on ships to prevent them from spreading invasive organisms all over the world. Somebody had a bright idea, and they went and built some equipment, and they tested it on real life organisms, and they showed that when the equipment was done with those real live organisms, they weren't alive anymore. And it was done quite cheaply. It was cost a couple of $1,000 to prove that the idea worked. The problem with that is, yes, it costs a certain amount of money, but to get to a final industrialized product, you've got certain steps, and those are very dramatic steps. So the first one is to go from a proof of concept idea, something that just basically works, to a fully functional prototype. In other words, something that does what the final product is going to do. And it turns out, approximately, these numbers are always approximate, but they do paint a picture. It'll cost you 10 times as much to make that functional prototype as it did to make that proof of concept prototype. So you think you've got a product? No, you don't, because all you've got is something that works. It might work very well, but you can't sell it to people yet. You can't even build it in a factory yet. Your next step is to come up with a prototype that's fully representative of what you're going to be selling people. And guess what? It costs another 10 times what you've already put in just to get to that point. Once you've got that, you realize that's not something that you can build in factories and just roll out to people. You've got to get something which is now completely representative of what you're going to be building in a factory. And it's times 10 again. And then, you haven't got the factory yet. You just got to start making the stuff. You've got to get them out and serviced in the field and reliable and maintained and everything else. That's industrialization process. It's going to cost you 10 times as much again. So here's the thing. 10 times 10 times 10 is 10,000. If you spent a small amount of money here, 10,000 Rand, to get your proof of concept that works, 10,000 times 10,000, is that 100 million? A lot of money to get to the industrialized product level. And this is why I say, this is where great ideas go to die. You may have heard in South Africa about the electrical car that South Africa was developing, a car called the Joule, very interesting vehicle. Looked very good. Then there was the pebble bed modular nuclear reactor, which was going to be a revolution in nuclear power. Actually, that came before the car. Very interesting development. It also died at this stage. The idea is still alive. It's being pursued in the US. But the point is, there was no money in South Africa to get it to this step. Developing products is insanely expensive. Developing products when you don't already have a product line building cars or nuclear reactors or whatever it is that you want to make, aircraft or something, is basically impossibly expensive. That's why I say great ideas die at this stage. So where does simulation come in? Well, not immediately obvious that it contributes to this project, right, to this the dilemma. But this is exactly the framework where I heard this for the first time. It was a conference on integrating CFD work and experimental work. And the point here was, if you can get these numbers down, the times 10 number, if you can get that down a little bit, it makes an enormous difference. It's not so important to get it down at this stage, but you need to get it down at the later phases. So of course, times 10 is just a very loose thumbsuck. If you're developing spacecraft, that could be 15. If you're developing coat hangers, it could be 3 or 4. These are just to give you an idea of where this is going. But if you can get the number down from 10 to 7 or 8, because you've got less failed development, you've got less failed prototypes, you don't spend quite as much time in the later phases correcting mistakes that should have been corrected earlier. It makes a difference between a viable product and a product that's not viable, because you may be spending 70 million instead of 150 million on the total development of the product.
Charles, there's a question from Rockefeller.
Shoot. Okay.
He says this is more of a broad question. How is bias handled when doing simulation? For instance, on product development. I'm not quite sure what he means by that. Maybe he'd better.
I think he needs to explain to us what kind of bias he's talking about.
Yeah.
Okay, maybe I'm gonna speak it myself. Is that okay?
Yes.
Yeah, I'm trying to take, for instance, a case where we are testing a product. We are doing some simulation, and we end up to neglect or to omit some cases because we think this is not really important. And let's say, for instance, there are products that we develop out there that's when going to production, they becomes biased against women, for instance. That's one case. Maybe because when on different phase of the product development, we didn't take into account such consideration because we thought maybe this is just going to work. Now I'm biased towards a certain class or a certain event or a certain scenario. That's what I mean by bias. And how do you handle that and when doing your simulation? Because to avoid bias, it would be great to test every single case scenario, I believe. I don't know. So
yeah,
testing every single case is also expensive. So
yeah. So this is actually, I think we can talk about this a little bit on this next slide because it addresses some of that. You've got to start broad. I think this is what you're talking about. You want to start your simulation process broad. In other words, explore. We talk about the design space. Explore your design space, all the possible configurations. And you would typically like to do that with cheap techniques. In order to narrow it down to the things that you know will work. So obviously, I think you were talking about men and women there. I'm not sure that actually helps here in this particular context. And I think it's very much product specific. But I think the broad idea is right. You might have some prejudices about how you would like the final product to look. But you want to delay that decision until you've got some pretty good information about about the implication of exploring different options. So you start broad, and then you narrow the product, and then you narrow your analysis, your investigations down into something which is more specific. Does that answer what you're asking?
Yes. I mean, the whole point was about how to narrow down the design space, actually.
Yeah. So you start broad with your approximate techniques, and only experience can tell you the extent to which you can trust your design methods, your approximate methods. They're not going to give you precise numbers, but are they going to give you a correct ranking? Are they going to say product A is going to be better than C, but worse than D? Even if the actual numbers are not that quite right. So we very early on in the days in the company that I was working for, when we were just starting to use CFD, we were faced with something like this. We really had to broaden the design space to find a configuration that was practical, because the configuration we had in mind, which could fit into the space that was available to it, could not deliver the performance. It was control authority on control surfaces of a flying vehicle. There was only so much space, and the concept that the original designers had come up with wasn't working once they tested it. And we used very, very rough techniques. I cannot believe that we got away with testing such rough techniques, but we had to, because we had very, this is 20 years ago, so we had very weak desktop workstations, PCs, available for doing our CFD. There was no parallel processing available to us, and very little memory. So we made conscious decisions to use very coarse simulation techniques to try and narrow down that design space, with the knowledge that much more detailed analysis and testing was going to come down the line. And it worked. It worked an absolute charm. And it's a very valuable technique, but you've got to understand what you're doing, that you're starting off broad and imprecise, and you're going to narrow it down to something that's much more precise.
Okay.
So yeah, this slide kind of illustrates that idea. So this is a very simplified, different look at how a product development might proceed. And the first thing you find here is you don't go from an idea to a fully validated simulation in a way that rather answers your question as well. And this is what we also deal with. We're trying to explain to our users at the CFD. You don't go from a simple idea to a very complex simulation. There's a very long path that follows to get there. So in the industry product development environment, this is more or less, and it's not just limited to product development. There's a lot of other things research related that this may be relevant to, even if you're not engineers working in product development. But the classic one is a bunch of guys sit around a table for lunch. Somebody has an idea. Somebody pulls out a pencil and takes a napkin off the table or the back of an envelope or something, and you do a quick calculation to see if it makes any sense or not. Is this going to work or not? And the idea starts to look quite good. Yeah, it might actually work. So your next step is to take your textbooks when you get back to the office, and you look up the formulas to see if you remembered them correctly, and you take some of the more complicated methods, and you actually work that out. Is this likely to work or not? How big does it need to work, or how powerful does it need to work, or whatever it is that you're dealing with. Then the wonderful thing about modern technology is about 40 years ago, we got spreadsheets. So now you take your classical calculation, you put it into a spreadsheet. So now you can, without having to work through cumbersome calculations over and over again, you can start running comparisons. So this is almost your first really coarse simulation case of shooting broad through the design space with methods that you don't entirely trust, but they run in seconds or microseconds. You start building up an idea of what that design space looks like. And then you start moving into simulation. And this is where the thing, of course, starts to become a loop, because these methods feed back on themselves. But a typical product development work would run something along the lines of, you do some simplified simulation, it looks good, goes out to the experimental department. In the meantime, you've got lots of people doing more detailed design work. And you also start doing more detailed simulation work. You get feedback from your simple experiments. You stick them into a more complicated simulation. If you get your thing looking as if it's more and more likely to work, you go and do some more sophisticated testing with higher precision models, whatever they may be. And then at this point, you start to get to a point where, okay, this is going to work or it's not going to work. If it's not going to work, you go back down here and you change things until they do. But you've got to a point now where you're starting to think that, yes, this looks like it might work, but now we've got to get this out the door, got to qualify it. And here you might do some very expensive testing to prove this is like a flight test of an aircraft, or a whole flight, several thousand hours of flight testing on an aircraft or something else. And some of it you can do with some very, very high precision validated simulations. So you make very, very sure that this is a simulation that you will believe. In the nuclear industry, if you change software versions, you need to demonstrate that it's still reliable. If you stick to the same version of the software, they're prepared to accept your answers for certification purposes. If you change your software version, you've got to go through the whole process again. So all of this that's outlined in red here, it's got a red line around it. This is stuff that's extremely expensive. So what you're trying to do with your development process is to bias your simulation process towards a simple. Make all your mistakes down here so that you've got fewer mistakes and things up there. It's what you're trying to get to. Make your mistakes. Make your mistakes when they're cheap to make. Don't make them when they're expensive to make. So the underlying concept here is that your precision of your simulations has to escalate as the project progresses. A concept that's turned out to be increasingly useful but very, very difficult to implement is something we call simulation-led design. So this is what happens in an old-fashioned company. You've got a design and development team. You come up with a product. You think you've got it right. You release it for testing. It fails the testing. And then you call in the simulation engineers and you ask them, why is this failing and how can we change it? Now, of course, these simulation engineers have been sitting here twiddling their thumbs all along, looking on in horror as the design and development process proceeds. And then the failure in testing comes as no great surprise, but then you get called in right at the end to try and do something to fix it. I've been in this situation several times. It's immensely frustrating. So the concept of simulation-led design is before you do any detailed work on the product, you start simulating. It might be very simple simulations, but you start off with a simulation so that you bring in your simulation at a much earlier stage of the process, right from the start, even before a lot of the other detailed work. Now, the interesting thing is this may not be faster or cheaper, but it can get you a product that's much better, and it can minimize your chances of failure. It's very, very difficult to get an established company to change from this to this because they've got a certain way of doing it they've developed over a lot of years, and for good reason they trust that method. It wasn't too difficult to persuade them to add in something else to help them fix problems, but to change this whole philosophy around is very, very difficult, and it's one of the challenges of this kind of environment today. Right, to summarize this little lecture, simulation is everywhere. It's used widely in more or less every field of human endeavor. Don't fall into the trap of thinking that everything is about simulation. It's not. There's lots of other things that go into it, any kind of thing that you're dealing with, but the simulation is increasingly important, and people realize this. You cannot replace your experts who know whatever you're dealing with very well. It doesn't matter if you're designing cars or boats or airplanes or computers or whatever. Your experts know what they're doing. And if they know what they're doing, they're very keen to get additional insights. And this is where you come as a simulation person. You support the experts with good simulation results. And then eventually you find that they actually fight for you in the company because they realize how much better the simulations are making them look. This previous slide that I showed, integrating the simulation with other processes, is tricky. It is really difficult, but if you're trying to get anywhere with simulation practice, it is absolutely crucial. Right, so hereby endeth this lesson. Any comments, questions, please? Everybody asleep? Do you want to do a 5-minute comfort break?
So maybe I got a question.
Yes, shoot.
So logically, I tend to think that sometimes making assumptions about the model or the product you're developing can also help narrowing down the design space. I'd like to know whether from your experience you have encountered cases where making assumptions has revealed not to be a good thing to do.
Yes.
You cannot get away from making those assumptions. You know, you don't want to find yourself with an impossible design space. You've got to narrow things down. This is where experience, of course, comes in. I mean, there's another heuristic. It's that you make all the big mistakes in the first 2 weeks of a new product. So for the next 10 years, you end up making all the small mistakes, but the big mistakes all happen in the first 2 weeks. So you have to question your assumptions at that point. And this is where, if you've got a process going whereby you can get simulation results quickly, early, even if they're not very precise simulations, then you've got a chance of minimizing your chances of making bad assumptions at that point. But of course, you can make really bad assumptions at this point, and it ruins the whole project. But the more you know, the more you can simulate, the more you can simulate quickly initially. And that only comes from actually taking a bit of a run at it. In other words, you've got to spend a couple of years building up a team that can do simulation work. The better your chances of avoiding those upfront mistakes. But yeah, incorrect assumption upfront. Look, remember what you're doing with developments like this is you're not choosing between option A and option B, where option B is better and option A is cheaper. You've got to choose between different concepts where it's not so much how good the one is compared to the other, it's how good you can make it over the next however long time you've got to work on it. And you don't know how good you can make it. So a lot of the art in it is trying to figure out how much you can improve what you already have. How well is it going to develop? So you've got to you don't have the resources to develop each product or each concept. You've got to pick the ones that you're going to develop, but you don't upfront know how good you're going to be able to make them. Okay. Yeah, so Jack Stevens, very good question. Could you please give us a bit of an example of simulation-led design? I'm just thinking that you can't simulate before you design. I'd rather have simulation before testing. These things run concurrently. They necessarily have to run concurrently. Simulation-led design would be, the crucial thing is to not inflict on your simulation department something which cannot work, but which cannot be changed. And this is actually what you find all the time in practice, is because the design office, it's also got limited resources, they will essentially do their best and essentially freeze what they've got. And then they go to simulation and say, prove that this works before we test it. And if you then prove that it doesn't work before you test it, you're actually quite unpopular because it's become rather too late to test. And this is what you're trying to avoid. So exactly the structure of how you fit in, where and how you fit in the simulation is crucial. The important thing about the simulation at this point is in simulation-led design, you can still change things before you go to testing. You don't want to test before you've simulated. You really want to test. You really want to simulate before testing, but also you'd like to have quite a high certainty of a design working before you commit to a lot of effort on the design up front. So you'll find that in, for example, aerospace companies and in the companies developing racing cars, for example, you do the simulations before you start doing the detailed design, because very often you don't need a lot of the detailed design before you can get the performance estimates. So you can start developing the bits that affect the performance a long time before the design of the bits that don't affect the performance so much starts because it can impact them. So essentially, it very often means bringing the shape under the control of the simulation group rather than under the control of the design group. Okay, anything else?
There's another question just before that, Charles.
What's the acceptable error scope for simulation that deals with human lives, such as failure analysis? Well, there's no such thing as zero error. There's always such things as safety factors. This is the question of appropriate quality control. So if you're doing failure analysis after something has failed, then that's very different from doing a failure analysis before things can fail. The important thing is you have to know what the error is. If you know how big the error is, then you know if your error is acceptable or not, because you'll be able to essentially put error bars on your results. In other words, a level of precision. And it varies. It really varies. But when you start dealing with human lives, then obviously your error bars get very narrow. And you have to err on the side of being conservative. If it's a design which does involve human life, but there's a lot of testing to come, then this is not important, because the testing to come before you release the product will be highlighting if you've got made a mistake that basically endangers human life. If you don't have that, and a lot of the nuclear industry is like this, if you don't have that, your acceptable error scope is extremely small. In other words, the nuclear simulation codes are subjected to extremely stringent quality control and checks by the certifying authorities, Nuclear Safety Council. There's an International Nuclear Safety Council. So you cannot use, for example, software in nuclear reactor design that does not pass, that has not been approved by those authorities. Anything else? So I see we've got 20 minutes to go. I'll just have a swig of water and then we'll go to do the last bit of CFD. So this is lecture 1.3. And so now we get more into fluid dynamics. And you should be able to see that. Fluid, this is now we're getting into the different modes of fluid dynamics. A bit of the history here. The first CFD as such was actually being done in the 1950s on numerical weather forecasting. Simulation work, numerical simulation work on computers started especially essentially during the Second World War with the development of nuclear weapons. So the first digital computers were developed and used for simulating those nuclear explosions at a very coarse level, I must say. But then immediately after the war, interest started on trying to see if you could do a systematic weather forecast. In other words, not just based on the experience of the forecaster, but actually based on the underlying fluid dynamics equations. And this was already attempted in the 1950s, and it was quite difficult to get to the point where it took less time to simulate the weather than it took for the weather to actually happen. And although it initially looked very good because the concept is sound, it soon turned out that the kind of resolutions that you could do in the 1950s, the kind of grid resolution, was of such a coarse nature that you were not getting very accurate results. So numerical weather forecasting obviously got refined, got better and better and better to the point where it is today as computer technology and software technology improved. But in terms of using computational fluid dynamics in other fields, it started with the use of numerical aerodynamics in the 1960s. So already by then, people had worked out how to deal with simplified fluid dynamics equations, but there were no computer programs to do it. So these had to be developed, and the computers to actually do this had to be developed. So very simple numerical aerodynamics, ignoring a lot of the effects of the real Navier-Stokes equations, became possible in the 1960s. Also even in 3 dimensions, not just 2-dimensional methods, although 2-dimensional methods were the workhorses of that time. And then simplified and better methods for the Navier-Stokes equations became available in the 1970s, and it became pervasive in the 1980s. By the second half of the 1980s, there were commercial computational fluid dynamics programs, and today, of course, there are very, very many, probably 100 or more commercial CFD solvers on the market, and lots of other research ones which are not freely available. That's a very short history of it. So I'm just going to run through different types of simulations. So this is quite a good illustration. We've got an identical situation. It's just a YouTube video. It takes the usual time to load. These are identical simulations. It's uniform flow, inlet flow, flowing past an obstacle. In this case, a cylindrical obstacle. And you can either do it steady, which means you drop the time-dependent terms from the equations, or you can do a transient, which means you take into account the unsteady effects. And what you see is something completely different. So superficially on the upwind side, things look more or less the same, but in practice, you get this oscillating flow. And this is something that should be familiar to everybody. You get this more or less anytime you stick a cylindrical object in flow. You get a humming noise, a vibration. Industrial chimneys have got these helical protrusions fitted around them to break up in 3 dimensions those vortices. A lot of radio aerials on cars, you'll find it's a piece of wire that sticks out from the roof, and it's got a bit of spiral wound thread or something around it, which does the same thing. Lots and lots of places where you find these unsteady shedding of a wake. It's awkward because it's noisy and it induces vibrations, but it's very much a real effect. And if you didn't do transient simulations, you wouldn't expect it. So this is the next one. So we can distinguish between compressible and incompressible flows. So we've got two identical situations run on the same computer software with the same computational mesh with the same fluid, but they're running at different Mach numbers, different speeds essentially. So in this case, your onset flow, the one on the left here, your onset flow is at about 80% of the speed of sound, Mach 0.8. And in this one, it's at a very low Mach number, Mach 0.15 or so. What we're plotting is the dimensionless pressure coefficient. In other words, we remove the dependency of the speed from the pressure, so that we can look at the pressure coefficient, which is a dimensionless number. And we see that the two solutions don't look at all like similar. The pressure is much lower over the upper surface in this so-called transonic case. And then there's a very abrupt transition to a higher pressure, a so-called shock wave. Depending on how resolved you make your model, that can be a very, very sharp discontinuity in the pressure. So the difference here was purely the compressibility. This flow is compressible. That flow is not compressible. It does not take into account the compressibility of the fluid. It doesn't make shock waves, and it also produces less of a low pressure area.
Charles?
Yes.
Luciano asks if you should always do steady simulations first before doing transient, or is not necessary.
Nearly always. Nearly always. But the reason for doing this is, remember I said you move from simple to complicated. You don't go the other way. And it's much, much, much more demanding to do transient simulations than to do steady simulations. You know, there's a temptation, and you find it actually in some of the older CFD literature and so on, which is that you should do everything with transient equations. And if it's steady flow, if it's a steady situation, if it is in real life, it's steady, it will converge to the steady state solution after some time. The problem is that some time is a very, very, very long time. The difference between doing that and basically making the equation steady by removing the time dependence to start with, it could be 10 times, 50 times around there faster. It's an enormous difference. So if you're doing your initial rough estimates, you will be doing steady analysis. Remember that's the slide in the previous lecture where we had the product development process. You started off with steady simulations. You don't start off with transient simulations if there's any way of possibly avoiding it. Now, some things are inherently transient, things that move. You know, for example, you cannot do any form of steady simulation of the flow inside an internal combustion engine in a car. Steady flow is just not defined. It's just not relevant because everything is changing all the time. So you can't do that there. But wherever you can, you will do steady simulations first. Steady is not the same as laminar. And this is one of the things that newcomers to fluid dynamics need some kind of time to absorb. An unsteady flow is not necessarily a turbulent flow. A steady flow is not necessarily a laminar flow. It depends really on the time scale of things that change. So in other words, you can take your time averaged turbulence influences and get something which is quite useful because your turbulence might be operating at very high frequencies that you don't notice. But in real life, they do look very different. So this is a steady flow solved with a turbulence model. And it looks nice and smooth. This is a transient flow solved with an eddy resolving turbulence model. And you can see there's a lot more going on there. The average picture looks like this. This is the average picture. If you took a photograph of it and left the shutter on the camera open for a couple of seconds, this is what you would see. If you take an instantaneous photograph with a flash, for example, you get something that looks completely different. So it's, it's quite important to know what you're dealing with. Some flows are inherently transient and some flows are inherently reactive. So this one here is a fire simulation. It's a very, very simple fire simulation. But fire simulations only make sense if they're unsteady. And most of the time, they only make sense if they've actually got the mathematics built in to resolve all the small eddies in the flow. So this is just a tutorial case, a very simple tutorial case from a very interesting CFD, open source CFD program. Andrew, help me, I've forgotten the name, the fire one. FDS, Fire Dynamics Simulator. It's formulated exactly to model fires. It's so involved to model the chemical reactions and combustion, and then the resulting turbulent flow and convective flow that comes from that, that it's worthwhile to use a special program just for this. And FDS is quite a remarkable piece of software. And it's another piece of very good open source software. Right, so this comes from another one of our favorite open source software products. It's a thing called Mfix. It's a multi-phase with phase exchange simulation program. And it's specifically developed for the simulation of multi-phase flows. So the thing that's modeled in this picture, in this video, if it ever plays, is a so-called sprouted bed, where you've got a container full of particles and you blowing a jet of fluid through those particles. So there are different types. But this is the sprouted bed version, where it makes a bit of a jet, which basically mixes up the particles and brings them in contact with the fluid. So there's a lot going on here. There's fluid dynamics going on, and then there's also particle dynamics. This kind of thing is enormously demanding to simulate, but fortunately these days with parallel computers, it's possible to do them. So it's a subset, if you were, of computational fluid dynamics, but it also includes the solids. Right, this is one of a boat, a double-hulled boat subjected to waves in the ocean. So this one, once again, there's a lot going on here. There's aerodynamics above the water surface on the superstructure of the boat. Then there's all sorts of hydrodynamics going on underneath. And at the interfaces of these two, you get you get the waves forming. So there are waves due to the motion of the boat through the water that makes its own wave system. But then it's also being subjected to the waves on the surface of the water. So a lot going on here, and this is essentially an example of a CFD solution with moving meshes, because you need to use the moving meshes to simulate the motion of the bodies. Right, I think we've had this question, how good is good enough? And the answer to that is fit for purpose. What are you trying to do with the answers? And as some of our questions have alluded to, if you're dealing with human life, your purpose is very, very strict and you need very high precision. It means you've got to take more time and do a lot more experimentation and testing to make very certain that your answers are reliable. But sometimes it's not like that. Sometimes you need faster answers and they don't need to be so accurate. So this is where you cannot let perfect be the enemy of good enough. In other words, you don't have to do a perfect simulation for it to be useful. So the question of narrowing down your design space, you've got your design methods, which are based primarily on fast, easy, basically giving you fast and easy methods for ranking design options. You've got your research methods, where you're trying to understand what's going on with the physics. And this may take you to very high precision. You may not use all the high precision results, but you're trying to understand some fundamental physical phenomena. And then you've got your qualification methods. Can you rely on these answers? So that's the kind of thing you get in, especially the nuclear industry. Right, just to summarize today's lectures, CFD, Computational Fluid Dynamics, a very, very broad concept. There's a lot of different types of physics that you can model, different methods that you can use to approach it. Very important to remember that simulation work has different purposes, and together with that, different levels of desired precision. Right, so I think we'll call it a day at this point. Any questions or does anything else anybody would like to discuss?
There's a question from Khalid.
Okay, I have a question. How do you make sure that the result you got is a physical phenomena and not a technical problem? Man, is that ever a good question? Yes. It's very important to make sure that. Remember, I remember I gave you that example of you've got different methods, your simplified calculations, your simulation methods, your experiments, and your field results from the having whatever it is operating in the field. And you've got to make sure that they all tie up, even if the answers are not exactly the same. That's how you make sure. You use different methods, because it's very easy if you're using one method only to have a technical problem and not be aware of it. There's lots and lots of things that can go wrong with more or less every imaginable type of experiment, and for that matter, every imaginable kind of simulation. Maybe run it multiple times. Yeah, but with different questions run it multiple times in different ways. It doesn't help running it well, if you run it multiple times with the same parameters, you must get exactly the same answers. If you don't, then obviously you've got a problem. So that's a valid answer in a way. If something looks wrong, do it again, provided it's not something that kills people while it's going wrong. You run it again and you see if you get the same answer again. If you get the same answer again, you've got to dig deeper. You've got to find other methods. But it is really important to understand that you've got different methods. You cannot rely on a single method. You know, never expect all your results to be identical. They don't have to be, but they do need to lead you in the same direction. Any other questions?
Yeah, Charles, it doesn't seem to be the case. And good afternoon. Sorry, I missed the beginning of your talk for other reasons. Yeah. So if there are no more urgent questions, I mean, everybody will have the opportunity for 2 weeks to interact with Charles. So please make use of the Moodle facilities, or just try not to forget a question until the next lecture. And Charles, thank you very much for a great introduction into fluid dynamics. I really enjoyed the parts that I could see. And please don't forget that tomorrow morning we start again at 9, we will start the third series in the morning and the fourth series in the afternoon. So be ready for tomorrow morning. So I wish you all a good afternoon and a good evening. And Charles, again, thank you very much for your time and for the very nice lecture. Yeah, and Ilya, thank you very much for introducing Charles at the beginning. Yeah, thank you.
Thank you.
Before you go, there was just one last question that popped up.
Oh, I see. Sorry.
We've still got a couple of minutes, so let's just take a look at it. How do you determine the optimum finite elements for the simulation to make your results accurate? You've got to compare it to things that you know. And that is actually a very, very good question, because you're talking about the optimum finite elements. In fluid dynamics, we mostly use finite volume methods, but it's relevant because you've got different types of finite volume meshes, and there are some finite element CFD codes as well. You do need to look very carefully at this. It's not always easy to know, but it really helps to compare it to things that you know. So when we found, for example, when we were training people to do computational aerodynamics, there've been a whole series of so-called drag prediction workshops where the researchers are given an identical model of a modern airliner, but not any particular model, but it's representative of modern airliners. And the different researchers with their different meshing methods and different CFD codes had to represent their results. And it's an absolute goldmine of information of answering that particular question for that particular field, because you can really see how well it's worked out in practice. But the general answer is compare it to things that you know. You have to compare it to things you know. Okay.
Okay, Charles. Thank you.
Right,
Thanks very much.
See you all on Wednesday.
Yes, yeah, thank you very much. Thank you. So
Okay.
everyone have a good evening. Yeah.
Bye-bye.
Bye, bye, thank you. Bye-bye.